Hello class. This lecture is going to be about absorbers and diffusers. We've already learned a little bit about these, but now we're going to learn more. Specifically, we're going to learn how to design them. First, sound absorbers. Spend a little more time on this. I wanted to start with fibrous absorbers. They are the most common. They're also the most effective at providing broadband absorption. Some of the other ones, the newer ones that we're going to cover here soon, they're more meant for what you might call specialty purposes, or they might be required because a certain look is desired by the architect or whoever owns what you're working on. But this one is most cost-effective, most common, provides a lot of absorption over a wide range of frequencies. That range of frequencies is dependent on depth. So here it says depth matters. It's the main point here. We've seen this figure before. We were looking at it more in terms of when we had ground absorption and we had a hard surface, we were seeing +6 decibels. And that was, we wanted to know why we saw that when we were close to the surface. We're looking at this for a different reason now. So there we were looking at pressure. Now we're looking at the particle velocity. That's this U. So here you'll see that once you get a certain distance away from the reflective surface, so here's that wave number. So that distance away is dependent on the frequency of the wave or the wavelength. So a bigger wavelength, we're going to need to be further away to get to the point of where there's significant particle velocity. And the way that fibrous absorbers work is that you have all these fibers, and the sound energy, that movement excites the fibers, and the fibers dissipate that energy into heat. So we need to be a certain distance away from the reflective surface for that phenomena to happen. So I think this just says that medium moves more further from the reflective surface for larger waves, that is lower frequency. So you have to have the fibrous material there to dissipate the sound energy into heat. You've seen this slide before. This is something you've seen before, but just with that last slide, I wanted to show again, when you go, so all these are going to give us good absorption at the higher frequencies. But as we get into greater thicknesses, the lower frequencies that it absorbs are extended out. So thicker, more absorption at low frequencies. That last slide is why. So we're about to move on from the fibrous. Before we do, I wanted to mention, so it's often fiberglass, sometimes it's mineral wool. It could be like a high density fiberglass or mineral wool board, that like the fiberglass panel that you might put on a wall. It might be panels that you line the inside of ductwork in a mechanical system, both to insulate it and to attenuate the noise. There's also closed cell or foam or closed cell type of liners. There's closed cell that you might put up in a room, and there's closed cell that you might put into ductwork. The closed cell doesn't absorb nearly as well acoustically as the fibrous does. So if you need absorption, whenever you can push it towards fibrous, you're gonna get more absorption per square foot if it's a room, or per linear foot if it's ductwork. The closed cell does have some advantages. dust doesn't collect in it as much. It's essentially better for the air. If you want good air quality, then closed cell would be better. And there are I've seen some school districts that will require all of your ductwork be closed cell. If it's like a locker room and there's going to be a lot of moisture in there, then that's a place where closed cell could be required as well. But the fibrous type is definitely by far the more common of the two. I've seen more of a push lately towards the closed cell stuff, but if you can get them to use fibrous, or if you can use fibrous in your own design, you're going to get more absorption. Some of the literature that will be published by the closed cell people will show similar or even better absorption in some octave bands. But if you look at where it's more critical at the lower frequencies, the fibrous would, in most cases, absorb significantly more, and at the very high too. You need to look at the whole spectrum. Don't just look at a couple octave bands and get sold on that. Anyways, I didn't want to spend a whole lot of time on fibrous. We already mentioned that some in the past. I wanted to spend more time on these newer types. The first one is the panel, or it might be called diaphragm. Sometimes it might be called membrane. But what you have is you have this thin solid layer, which would essentially be acoustically reflective, except for you have this cavity behind it, and it moves like a membrane, and that movement absorbs sound. It's a lot more tuned to a specific frequency. There's a resonance frequency where it will absorb the most. You're going to get a little absorption above and below this point, as you'll see in some figures coming up, but it's a lot more narrow band. So typically you fur that layer out some amount. You have a little bit of a gap between the backside, and then you have most of the depth is going to be a fibrous sound absorber, glass or mineral fiber. These dimensions on here aren't what you have to do, but this is might be a common one. This is the equation to determine the resonance frequency of that panel. This is in your reading assignment. So that resonance frequency is equal to 170 divided by, so we have the square root of the surface density. So note, this isn't the mass, but it's the surface density. And for this this is one of those equations where you have a number here, and for it to all work out, you just need to put in numbers here that are in the right units. So pound per square foot for your surface density. And then D would be your depth of airspace in inches. So you put those in using those units, you'll get hertz out for your resonance frequency. There are also figures like these. So you have the x-axis has to do with that surface density, or sometimes called surface weight. Down here we have it just in ounces per square foot. But up here, so plywood is probably the most common material that might be used here. So they have these lines here that correspond to standard plywood thicknesses. Our y-axis is the depth of that cavity behind. So you could do this forward and backward, but say you knew you had plywood, it was an 1/8 inch thick, and you're going to have a 4-inch cavity behind it. So right here, you would be, what would that be? That would be maybe about 140, 145, somewhere in there, hertz. You'd be between 125 and 150, more towards 150. That would be your resonance frequency. So these lines are your resonance frequencies. And it's maybe more likely that you would be going the other direction. You'd say, I need a panel that's going to absorb at 125 hertz. Usually these types of panels, it's like a recording studio. You have a very specific frequency that you want to take out of the room. So you've done some measurements, you know that's at 125 hertz. So you say, okay, I'm going to use 1/4 inch plywood. That would mean that I need to have it's probably like 2 3/4 inch depth behind. So you might want to use that equation if you wanted more precise numbers. This table can be convenient at times, but usually the equation will give you more accurate answers. You should know that, though, being where you are in your engineering educations. This figure plots actual data for panel absorbers. So we have 3 different types here. B and C are pretty similar. A is different. A does not have absorption. So it's 3/16 inch plywood with a 2 inch airspace behind, not filled with anything. The other 2, you just have a difference in thickness. So B is 1/16 inch and C is 1/8 inch panel. And then behind both of those, you have 1 inch mineral wool and a 1/4 inch airspace. So you have the panel, 1/4 inch airspace, 1 inch mineral wool. So a big thing to note here, so one, as we go to a thicker panel, the frequency drops down if everything else is the same. And then also note the big difference in the amount of absorption that's provided when you have sun absorption in the cavity. Here we're getting absorption coefficients of 0.6 to 0.65, when down here we're only getting it around a little above 0.3. That's the effect of sound absorption. So these last 2 types lead me to bringing up an important point. Like it says here, it is critical to know the backing and mounting method of sound absorption data. Now, usually, if there's some product or even just some common building material, there was a laboratory test done on it at some point. And that data is going to be published with a lab report, and it should specify in there exactly how it's mounted. I'm going to show you that there's even a standard for the different mounting styles, but it's important to know what your data has for the mounting. And let me talk about this data up here to demonstrate why that is. So you have a test done of sound absorption panel. It's just a 1 inch. If you look this up, you'd find out it's a fabric wrapped fiberglass panel, 1 inch thick. So it absorbs really well at mid and high frequencies, and then as you drop down to low frequencies, it does almost nothing. So this would be a fibrous absorber. And then here we have gypsum board, just 2 layers on studs, like your wall might be constructed of. And here is more like the panel or diaphragm or membrane absorber. You have a pretty good amount of absorption, significant amount, 25% is being absorbed down here at 63 hertz, and it's almost completely acoustically reflective up at these higher frequencies. So that's pretty typical for these 2 types. This one here, if you went and looked at that test report, you would see that it's A-mounted, which means it's surface mounted. And when it's done in a laboratory, they typically do this. Even if they're testing a ceiling material, they often do this on the floor. So it's often a concrete floor, and the material is placed on it through one of these mounting methods. In this case, surface mounted, so directly up against it, no cavity behind it. Now, say you were doing an acoustical model of some space, and you make some measurements, or you model this room, and you see that you have too much reverberation. So say you're seeing too much reverberation up here, the mids and highs. So you say, okay, I need to put in some sound absorption panels, and you say you have to put in 1,000 feet or some 1,000 square feet, something significant like that. So you put that in the model, you switch out the gypsum board for the sound absorption panel, and it brings all that down like you intended, but then you notice that the reverberation in the low frequencies increased. So you add sound absorption panels and the frequencies increase. That isn't what would actually happen. If you, like when you put a fibrous panel over on, for the most part, acoustically reflective surface, and we're even calling gypsum board in this case that, it's going to, like we said, it's going to absorb these mid and high frequencies. Then at lower frequencies, those big sound waves are just going to not even be affected by it. They're basically just going to go right through it. And that doesn't mean that it's going to reflect it back and it's never going to see this gypsum board. It is going to be absorbed by what the gypsum board can behind that panel. So what I would recommend doing in that case is like I did here, you put the two down that you're going to put the fibrous over the gyp board. If you did it the other way around, this would be a completely different story. You'd probably only be taking this absorption, not the fibrous panel at all. But when you have the fibrous over the gypsum board, the big sound waves pass through that thin 1-inch fibrous thing and they see the gypsum board. So this absorption quantity or absorption coefficient gets put here. This one gets put here. And at 250, the fibrous panel takes over and starts to absorb more. So I would essentially, in this case, just be using the max of the two of these when you have one over the other, or when you have a fibrous over a membrane. So I think this, we said this one here, so just a point that this essentially free absorption, you need to get the acoustics right in this space. All the walls are going to be gypsum board in a lot of spaces. This is just free absorption that you get. That is, it's actually hard to put panels in and get that absorption, right? You'd have to put in like a 4-inch thick panel to get to this. So this is free absorption. You don't want to ignore it in your analysis. It can be very useful. So you might be doing this manually, just with your own analysis. You get these lab reports. You need to go through all those considerations I mentioned. You also might purchase a very expensive acoustical modeling software package, and it's going to come with a library of materials. So a lot of different products that are available, and then just generic building materials that have been tested. And if you just use those, you're going to get that thing that I talked about where you replace gypsum board with sound absorption panels and you see an increase in reverberation at some frequencies, at low frequencies. So you're going to have to be aware of it in those software packages as well and create your own custom materials. It's pretty easy to do. Just make sure you remember this whole concept. So on to those mounting methods. Like I said, there's a standard. So A mounting is just surface mounted. A is common, C is common, D is common, and E is common. I don't see B or F all that much, but B here you have layered gypsum board and you're shimming up that panel on top of it. This gypsum board and that little shim isn't going to change much, but this is a mounting method. This type C mounting is a pretty common one. There's likely going to be a hyphen and a number after it. It might be C-50, so that 50 would be millimeters, meaning you'd have 2 inches, right? 1 inch is 25 millimeters roughly. So C50 would be whatever your absorption panel is. It could be a fibrous panel like this as well that's furred out, and then you have some less expensive sound absorption behind it, for example. That would be type C. And type D is like that too. just no lining there. Type E, this is typically a sealing treatment. So usually there'll be E400. 400 millimeters is 16 inches, and that is the kind of rule of thumb for what a suspended ceiling is going to be suspended below the deck. So there'll be room for structure, there'll be room for ductwork, conduit, whatever else needs to be hidden in that particular space. So know when you get, say if you get an acoustical ceiling tile and you get the absorption coefficients for it, it's likely tested in this E400 mounting. If you instead took it and mounted it A-mounted, say there's a gypsum board ceiling and you just want to come in and apply it to the underside of that, you're not going to get nearly the absorption that you get as you do here with this big gap behind. And when they test this, like I said, they'll test it on the floor and they'll block off the boundary around it. So you don't want sound getting in and getting absorbed on the backside too. It's just like it would be in situ. You'd have the sound passing through, getting absorbed. That's it. So good to be familiar with what all these are and make sure you account for that in your modeling. Now moving on to another type. This is the perforated panel absorber. So there are kind of two different panels you might come across like this. So this first thing we're going to cover, and the thing that the book gives equations for, is more where you have often a wood, just a piece of wood, and it has a bunch of holes drilled into it like this. And the main mechanism of producing the absorption is the Helmholtz. There'll be some liner in the back that has a similar effect as what we saw on the other slide, just increasing the amount of absorption. But a lot of the effect is Helmholtz. And there'll be some of these panels that just have a very thin fabric on the back side. And you might be thinking, like, how is that going to absorb anything? But it's more Helmholtz. There is actually a fair amount of absorption that comes from that. I'll talk about the other types soon. But so this is what it looks like up close. Some of these might be micro perforated. You might have really small holes. Basically, you won't even be able to see it. It's just going to look like a wood sheet. And so this here is something more of like a hole pattern like this. It looks for the most part like wood, but you can see that there are penetrations or perforations there. I'll throw in something about cost. Usually those fibrous panels, like say you just went for the cheap black stuff that you could put up on stage walls or in a movie theater where it's going to be black, you want black walls. You know, that stuff you can get materials for just, a few dollars a square foot. And it's really effective at absorbing sound. And then stuff like this might cost more like $35 a square foot. Some of it might be even up as much as high as $50. And it absorbs less. So this is something I come across in projects all the time. They want it to be as least expensive as possible, but they want a certain look. And if you can get the acoustics to work pretty inexpensively with just fibrous materials, but the aesthetic desires of whoever's project it is or whoever's designing it, those wishes to have it look like wood or look like just a nice clean white surface like drywall, those are the things that are going to drive the price up. I mean, not only do you have a much more expensive material per square foot, maybe 20 times as much, but it's also less effective, so you need more of it. But it's used all the time, like you see here. Here is the equation for the perforated panel absorber. So again, we have resonance frequency, we have a number in here that makes all the units work. So so long as you enter these in the units that are given here, you'll get the resonance frequency in hertz. This P1 is the perforation percentage. So you put in a percentage, so 99% would be 99, not 0.99. Usually it's not nearly that high. Usually for these it's more like 15% max, something like that. But it's the whole area divided by the panel area. So like percent open area, then that divided by, or multiplied times 100. T is the effective hole length in inches with a correction factor applied. So you have the panel thickness plus 0.8 times the hole diameter. And then D is the depth of the airspace behind in inches. Now this is the part where I talk about there's another kind of acoustical panel or treatment that might seem pretty similar to this, but is different. If you have, say, a sheet of metal that has a lot of holes cut into it, like if you've looked at a nicer speaker, like a big speaker meant for reinforcing sound in a large auditorium, it likely has a metal grill across the front. And obviously you want that to be acoustically transparent. So if it's something more like that, or like just a mesh or something that's clearly, the intent is for it to be acoustically transparent and let the sound pass through to get to the sound absorption behind, that's something else. There's a different method for that. So the acoustically transparent screen, that's what we can call it here, with sound absorption behind. If you were doing that type of a thing, the approach you want to do is the transparency approach, and then from that, in that you calculate an access factor. And that essentially is a quantification of how much sound is allowed to pass through that surface material that's essentially there for aesthetics or maybe for protection of the material behind. Like you might be designing say you're designing HVAC equipment, and a lot of times they come with a casing that's intended to attenuate sound. So you can put this close to the property line and still meet the noise ordinance. But inside of that, you're going to want in some cases they might just line it with fiberglass type of insulation, the fibrous insulation. But a lot of times it'll also have a metal layer with a bunch of perforations in it to protect the material. Silencers that might go in your HVAC system would have those perforations in it. Acoustical louvers for your HVAC systems. There are lots of places where you might have these things that are meant to protect and hold in place the sound absorption while still exposing it to the sound as much as possible. So the book, your reading assignment doesn't cover how to calculate for this. I have my own calculator that I created a long time ago. So the parameters are, if you Google those things about transparency index and access factor, you can find a way where you can make your own calculator like this. Like a lot of things, there's a table. So here you're getting the access factor for different transparency indices. So let's start over here. If you have these parameters here, like sheet thickness, the perforation diameter, and the on-center hole spacing. So these are used to determine the percent openness. So based on all of this, there's an equation. It uses some of these access factor coefficients. You use all that in that equation, then you can get the transparency. Actually, you do this to get the transparency index, and then you incorporate these access factor coefficients to get the access factor. If instead you just calculated the transparency index, then you could use this table. So say, like this one, we have 23% open area, these parameters, it ends up giving us a transparency index of close to 1,000. we'd be somewhere between these two lines. So if we were at, say, 500 hertz and below, so all these, let's show here, all these are 1. But then as we start to go up to higher frequencies, our axis factor starts to drop down, meaning the low frequency sound is just going to pass right through. The little bits of metal that are still there, the big waves, are just going to go right through it. It's not even going to see it. And then as you go to higher frequencies, the wave lengths start to get smaller, and they start to see those little bits of metal that's still there between the perforations. And that will reflect a certain amount of it back. So the more metal there is there, and the higher the frequency or the smaller the wavelength, the more that's going to be reflected back. And that's what this indicates. So here we're letting 100% through, 99%, then 94%, 82% through, 61% through. And up here at 1600 hertz, sorry, 16,000 hertz, we're reflecting back 80% of the energy. So that, I calculated, that's what this blue line is, for a panel that I had test data for. I just wanted to compare, see how well this matched lab results, lab measurements. And it was actually pretty close. So we'd have, if we're just talking about sound that's going to be allowed to pass through and get absorbed or not get absorbed depending on what the material behind can do, we would have a curve that would go along here like this, and then it, like around just after 500, it would start to drop down. So up here, the stuff that's not being absorbed is because it's being reflected back by that surface protecting perforated panel layer. Down here, it's letting everything through, but why this drops off is because of how capable of absorbing the sound, the fibrous backer is. That didn't come out quite right, but so we have a 2-inch thick panel behind. The panel is letting everything through, but that 2-inch thick panel is only absorbing 20%, 38%, I guess maybe closer to 35. So this part of the curve is dictated by the fiberglass behind it. So there'd be something like this for the fiberglass for what it can absorb, something like this for the perforated panel for what it can let through, and those combine to be this curve. And that matches the measured data pretty well. Let's see. Oops. So to calculate this P, this perforation percentage, the reading assignment has these 3 different equations for these 3 different configurations. Here you have circular holes in a grid-like pattern. Here you have circular holes in an offset pattern. And then here you have more like slats or bars. So just identify which one you have, enter the parameters like the diameter and the space between the holes on center, and you'll get the perforation percentage that you'll put into that equation. Again, there's a table. This table is only for panel thicknesses of 3/16 inches. So kind of more factors here. If you had, so say you had something with 2% perforation, so 2% open, and then you had a 2-inch furring strip behind it, then, and you were a panel of 3/16 inch, then your resonance frequency would be a little above 600. That's how that would work. You might go the other way, where you need a certain absorption, you know you have this thickness panel, you you can fur it out with 2x4s. So whatever that is, say you needed 200 hertz, then you see, oh, I need 0.3% perforation. Here we have another equation for slat absorbers. It's very similar to the one we had for the perforations that were circular. So I think everything is basically the same except for that number, right? Yeah. So just a little bit different for slats. I wanted to define this noise reduction coefficient and then talk about its application. It's a pretty simple thing. It's just the arithmetic average rounded to the nearest multiple of 0.05 of the absorption coefficients for a specific material and mounting condition of the octave band center frequencies of 250 hertz, 500 hertz, 1 kilohertz, and 2 kilohertz. So just simple average of the absorption coefficients in these 4 octave bands. I should have said that instead of trying to read through all this. It always is going to be in multiples of 0.05. So any material that can be absorptive, you could calculate a noise reduction coefficient for it. And so this just means, a lot of times you might need to take a logarithmic average in acoustics. So we're just specifying it's a simple, add the 4 absorption coefficients together, divide by 4. So this is a really widespread thing. I'm going to show that and talk about why a little bit more. I'll get to. There's a bad side to it too, though. I'm trying to figure out how to say that. There's a bad side to it, but let's look at the good side first. So the use of it is that it's primarily used for less critical applications for speech intelligibility. It's really useful for that because, so this is where speech is, where it's most critical to have clear acoustics, not having muddy reverberation to maximize speech intelligibility. So here you have a 1 number rating that covers that range. So if you have a basic classroom or you have office spaces, stuff like that, it's perfect for that. But we can hear down to 20 hertz. And there might be some, if you're doing a movie theater where you're going to have a lot of low end and explosions in the movie, or if you're doing a place where music's going to be performed or recorded or practiced, you have all that low frequency stuff. This does nothing to tell you how well a product will absorb those lower frequencies. So if you're doing something that's broadband or more critical, you don't want to just rely on this. And you'll probably have somebody on the team that wants to use a product and they say, can't we use this? It has really good noise reduction coefficient. And you have to say, well, yeah, but it's terrible at these lower frequencies, and it doesn't, this metric doesn't tell you anything about that. So we need to consider these lower frequencies because you plan to do whatever, music, movies. So in those cases, more critical or more broadband, you need to look at the 1 octave or the 1/3 octave bands, particularly the lower frequencies. But this is a really widespread thing, so lots of products are going to have, especially the ones that are really intended for those applications. So restaurants might be another good place where an NRC would be useful. But so acoustical ceiling tile, it's often, if it's absorptive, it's going to have an NRC rating. It's more likely you're going to have this, and it's probably hard to find the absorption coefficients in octave bands. So there are 2 different types of ceiling tiles, 2 common types. You have mineral fiber and you have fiberglass. The fiberglass is really sound absorptive. You might get 0.85, 0.9, 0.95. You can get really high absorption coefficients for fiberglass, but it's really transparent. It just lets sound pass right through. If you're going to be so if you have a classroom and you're putting a bunch of fan coil units, so some mechanical systems, you have one big air handling unit on the roof, and that just pushes air out to all the other places. Alternatively, you might divide up all the spaces into different zones and have a small fan coil unit serving each space or each zone of spaces. And often, so you'd want to put that out in a corridor or over a storage room or something like that. But sometimes it might be above a classroom. And if you did that, you wouldn't want like that high absorption level of the fiberglass stuff. You wouldn't want that because it would absorb sound, the sound generated by the people down in the room, but it's going to let that fan coil unit just pass right through it. It might be the same thing if it's the top story and you have the packaged unit on top, you have a lightweight roof, then, or say you even have a concrete roof, but the ductwork penetrates down, so the sound just breaks out of that thin sheet metal of the ductwork. Like in any of those cases where you have a significant noise source above the ceiling, then if you're going to have acoustical ceiling tile, then mineral fiber would be better because you get more moderate sound absorption, but you get the CAC is a ceiling attenuation class. This has more to do with sound isolation. We're going to learn about sound isolation. That's coming up next. So say the isolation of sound in one space from another space. So the ceiling attenuation class, that's something just specific for acoustical ceiling tile. A lot of times, say you have two offices next to each other, they won't make the walls in between full height. The walls will just go a couple inches up above the ceiling tile. So the ceiling attenuation class is a measure of how well a ceiling product will attenuate the sound, it'll isolate the sound, and it's for sound coming up and then passing down on the other side. So it's like a two-pass measurement. But generally, for mineral fiber, if you can get 0.7 and 35 or 40 or better for the CAC, so 0.7 for NRC, 40 for CAC, that's a good mineral fiber. It's kind of good all around. That 0.7 is really important. So here we have LEED criteria for schools. So our new Norma Bjornsson Hall is LEED certified. I think it's LEED Platinum if I remember right. But as part of LEED for schools, any space where the main purpose is instruction, you have to meet the room acoustics prerequisite. So there are prerequisites where you have to do it, and then there are also other ones that aren't required where you can get points for it, but you don't have to do it. So, but this one has to be done. So like the sound isolation one, I think that one is not a prerequisite, but you can get points if you meet all their criteria. But for now, let's just focus on this one. For room acoustics, you can do calculations to meet a certain reverberation time based on the volume. And it's a little bit questionable. Does this actually, by the strictest definitions, does this even apply to a space like this, a classroom space? Because it's a small space. It doesn't mean all those things like having mostly reflective surfaces, having highly diffusive surfaces, having all the surfaces being roughly the same. So it's not a diffuse sound field. So it's kind of hard to really apply a reverberation time to it, but it's still done. This is a really widespread criteria. It comes, although LEED stuff comes from an ANSI standard, which is even more widespread. But in any case, you can do all the analysis and do the measurements to show that you meet these reverberation times, or you can take option 2 where you just finish 100% of all ceiling areas, excluding lights and diffusers or grills in the HVAC system, with a material that has an NRC of 0.70 or higher. So if you just say all the ceiling is going to be acoustical ceiling tile, it has an NRC rating of 0.7 or better, you can meet this prerequisite for getting the LEED points. That's it on absorption. I wanted to now talk about diffusers. So first, again, is just something that we discussed way back at the beginning when we were talking about the nature of sound. Remember Huygens Principle. Every point on a wavefront is a source of spherical wavelets. That is a new point source. So here we're seeing something like a plane wave coming, and we distort the plane wave, so all we're letting through is this point. So we see here that this point is now, or it always was, but here it's going to be experienced as a point source. So that same principle can be used to create diffusion. If you have any type of big offsets, you're distorting that wavefront. So say you have a wave that's coming at this wall, and here you're going to stop this wave at that moment in time and start reflecting it back, but the rest of it's going to pass through until it gets to this wall. So at this point, like that wave let right there would be essentially a point source. So it's going to start to send out sound in, it'll essentially make all these edges line sources. So that's one mechanism of diffusion here. But then also when this sound and the sound from this, if they come out, say it's just meeting at some point out here, you're going to get sound from here and you're going to get sound from here. It won't be from the same original wave. It'll be from whatever one was ahead in time, this distance times, or yes, this distance. No, in time, it's going to be that distance divided by the speed of sound. So that's going to give you a change in time. I probably confused it all, but the thing is out here, you're going to get a reflection from this, and you're going to get a reflection from this, and they're going to be at different points in their phase. So you're going to get some cancellation there. And that can help to diffuse things as well. But look, in this design, they incorporated all kinds of these offsets, and that would have been, I guarantee you that was their purpose, was to just create a lot of diffusion up here. They have it here, they have it up here in these soffits. They have it here on the undersides of the balconies, just these thick things that diffuse the sound. So remember that. And then the other one that I wanted to show you is just a pretty interesting type of diffuser. It goes by two different names. These days it's mostly known as a quadratic residue diffuser, but the guy that invented it or discovered, developed the math for it, was Schroeder, so sometimes they're called Schroeder diffusers too. But they're based on quadratic residue sequences. So you have an odd, so you have this N, capital N, and you have, so 3, 5, 7, 11. If it's 3, whatever your N is, that's how many integers you're going to have here. And these are determined from this quadratic residue sequence. So actually determining those, not doing that here, we just have all these here in a table. But let's take this one. So let's say we're basing it off of an N17 quadratic residue sequence. So have that here. So what happens is these numbers end up, they tell you the proportions that your diffuser should be. It basically assigns so here we have a reflective surface. Sound would be coming from this way. We have all these wells. So it's, this here is 0, this is 1, this is 4, this is 9, this is 16. So all those the dimension is going to make an important, it's going to be important for the frequencies that this works at. But just to create the diffusion, to create this really good scattering at whatever that frequency is, we get the proportions of these different depths from that sequence. So a couple things to note. So it's symmetric. Like one, you can see it's symmetric. This side mirrors over to this side. And then also you repeat these. So the 0 here becomes the 0 here. So it's symmetric about the ends to those zeros. And they are periodic with period n. The more you can just keep putting these end on end on end. So it's likely going to be, if you bought one, it's going to be like from here to here, and then you buy more, or you have them in modules like that, so you just keep adding them. So I mentioned the quadratic residue sequence determines the proportions, and then the dimensions of the wells determine the frequencies diffused. So here you can say I want a n equals 13 quadratic residue diffuser, and I want it to be most effective at diffusing 600 hertz. It will diffuse a wider band than that. Like here they're talking about, so 300 hertz, the center is going to be 600, they're talking about from down 300 hertz up to 2000 hertz. So pretty wide range of where you're going to get some decent absorption, but there's still, if this, we're going to talk about how you can get more diffusion out of this in the next couple slides. That, from here down to 220, you still want to get, at these cutoffs, it's not going to be providing a lot, but it'll still be providing some. But you're going to want at these frequencies and definitely higher to take care of them with different diffusers. We'll show you how you do that in a minute, but just remember that the residue sequence determines the proportions, the wells determine the frequencies that are diffused. And this calculator is a free calculator. You can download it online. Just Google QRDude. I've used it in the past for designing these, and it worked well. I would demo it, but it's on my other computer. So I mentioned that it covers a fairly wide frequency range. Like here we're seeing, so the total here is from 80 to 20 kilohertz. So 80 hertz to 20 kilohertz. This is the upper end of what we can hear. There's still, from 80 down to 40 and 40 down to 20. There's still 2 octave bands down here at which we can hear. And this isn't, they're not claiming that it can provide any significant absorption for us there. But what you can do, and what they're doing here, is they are nesting one quadratic residue diffuser into another. And actually then they're nesting that one into a really big one. So this small one, you're getting the high frequency diffusion. Then that nested into this one, you're getting the high and the mids. And then these nested into here, you're getting almost the full frequency range of what humans can hear. So here we see a couple images of, so this one is just one nested inside the other. That'd be like this nested inside of this. And then here we're seeing that actually installed in a space. This is a really common diffuser in recording studios. Often the back wall will be this type of diffuser. Very common. It's kind of a cool theory behind it all, I think. Anyways, that's it. We'll see you soon.